So, okay. Any questions from last time? Everything's clear? Things good? Okay. So, my hope is that today I will finish the introduction part to quantum mechanics, and hopefully from next time we can actually do some crypto. Um, okay. So last time we were looking at the Stern-Gerlach, right? So we looked at how the Stern-Gerlach works. We saw how we can define the three Pauli matrices, right? And then this was an exercise, which was that. So the sigma x, sigma y, sigma z. Let these be Pauli matrices, and we wanted to show that sigma x, okay, get this right, sigma z, sigma x is 2 iota sigma y. Okay, and similarly the other combinations, so sigma y, sigma z is 2 iota sigma x, and 2 iota sigma z, sigma x, sigma y. Okay. So last time I said that these two don't commute, right? And so therefore you get a different measurement result. It disturbs the experiment, but this gives you quantitatively what the commutator is. Um, and then you can also check that, for all, so for tau in sigma x, sigma y, sigma z, tau square is identity. And so that's one. The second is determinant of tau is -1. And third is that the trace of tau is 0. So these are traceless matrices with opposite eigenvalues, and they square to 1. Okay, it's a very simple exercise, but just to make sure that you're on the same page. Okay. And then one question which I thought maybe might have arisen in the minds of people was that why is it that we're using SU2, right? Why, there's like some notion of directions X, Y, Z, and we're still using SU2. SU2, SU2, right? Special unitary group, so determinant one. So the reason for this is that there are many deeper reasons which we'll come to, but one of the reasons is that the Lie group of rotations, so the Lie group of rotations in three dimensions. Uh, well, I wanted to say the generator, okay, of rotations in three dimensions, right? So that's SO3 is isomorphic to that of SU2, special unitary group, right? Okay, and so formally it's written as follows: that this script little o3 is isomorphic to SU. So that's the Lie group. Okay. So there's a strong correspondence. We close the door. Okay, so there's a strong correspondence between these two. And one nice way of visualizing it, which I think is worth noting, is the following notation. So this is basically what's called the block sphere. Right? So the notation is what a block sphere is. So you consider the parametrization theta phi do you want to keep the door open? Is it too stuffy for people? Ah, the fan. Okay. Yeah, you can just turn off the regulators rather than finding which fan it is. It worked. Nice. Okay. So theta phi we define as follows. Right? So cos theta by 2, 0 plus sine theta by 2. And then there's e to the I phi, 1. Okay. So, theta and phi has, the usual range. So theta goes from 0 to pi, and phi goes from 0 to 2 pi. Uh, okay. And the nice thing here is that if you use this representation, you can sort of see that you actually get, so, suppose we plot this, right? So we have the z-axis, the x-axis, and the y-axis, right? And we take the angle from the z-axis to be theta, as is customary. And its projection on the xy plane, you look at the angle from x to that projection, that is given by phi. And then you can check that indeed for all the various values of theta and phi, like the extreme values, you would get that this along the z-axis, this vector will correspond to the 0 vector. The downwards vector would correspond to the 1 vector using this parameterization. Okay. Um, so you can write it more carefully. So you can say that the 0 vector, yeah, maybe let me write it more formally. One can check, right? So I'll just write it as a note. So one can check that 0 is essentially, so 0 in the SU2, the way we studied it. So this corresponds to 0 comma phi. So because at the pole it doesn't matter what phi is, right? It's going to be the same vector. 1 is going to be phi. Uh, Unless I mixed up my parameterization, it should probably be okay. Uh, no, pi by 2 would. Uh, no, but I wanted. Yeah, yeah. I was just checking the other ones. Yeah. Okay, so by this parameterization, you'll have something like, let's have this here. Right. So the top one is 0, and the one at the bottom is 1, right? And then one can also check the other ones. So you can write plus as pi by 2 comma 0, pi by 2 comma pi. So just go to the opposite, right? So this is the x-axis, so this is what would be plus. The one behind would be minus, and then y would be plus tilde, and the one behind would be minus tilde. As you can check that it sort of works. So that gives you the connection to the so it basically relates SU2 to the physical world like we wanted to. And this is actually a little bit deeper, so I'll not go into the full details. I'll probably leave it as an exercise. So there's, even when you have mixed states, which I haven't discussed yet, you can have an interpretation in terms of the block sphere by using the Pauli matrices. So this will probably be an exercise. Okay. So this was just to complete the discussion from last time. And we can now move on to the next part, which is the uncertainty principle, right? So I basically only briefly mentioned that if you measure one observable and if they don't commute and you measure the next one, then it can influence the outcomes, right? But one can make it more quantitative in terms of this commutator, like the way we wrote it. And this is called the uncertainty principle. So there are many ways of deriving it, and there are many versions. We look at the among the earliest one. Okay. Um, so we need to start with a fact, which is yeah, maybe the numbering changed in the notes, but okay. So the fact is the following. So suppose I maybe I should take some notes. So suppose that O1 and O2 are emission, okay, in CD firstly. Okay. Now, if O1 and O2 commute, okay, this is a well-known fact. Um, then you can basically there's a single basis that diagonalizes all of them, right? So then there exists a basis V1 to VP. This is the basis, orthonormal basis, orthonormal. Sorry, I messed up the writing. So there's an orthonormal basis in which such that O1 is lambda I 1 VI and O2 is some and O2 is lambda I 2 VI, right? Okay. Um, uh, do you guys know the proof? Yeah. Okay. So I will. Yeah. Maybe I'll just briefly mention the idea very quickly. So suppose that you have. So I'll not give you the full proof. I'll just quickly tell you the idea. So let's uh, to be sure that it sort of makes sense. Okay. So the idea behind the proof. Oh shoot. Is something like this. So you say that suppose, so consider V to be an eigenvector, be such that, so let V be such that OV, which one do we want? The first one. Okay, so let's suppose O1V is some lambda V. Okay. Um, now, so we want to note that O2V is also an eigenvector. O1 with eigenvalue lambda. Okay. So why is that? Um, because so we start with O2V, okay, and we act on O1, yeah, and then because O1, O2 commute by the hypothesis, right, we can write this as O2, O1V, right, and this we know is what? This is already lambda, okay, right? So, this thing is an eigenvector with eigenvalue lambda. Which is what we wanted to prove. Okay, good. How does it help us? It basically says that you can pick. So suppose O1 is an eigenvector, right? So I write it in some eigenbasis, and it will have some block form, right? Suppose this is the lambda eigenvalue space for eigenvector. Sorry for this. So this is observable O1. Okay. Then all that we are saying is O2 is only going to move things around within lambda if you're in this eigenspace. Okay. So any vector within the lambda eigenspace will be mapped to another vector in the lambda eigenspace of O1. Okay? So this is what the fact says. And then what that means is you can restrict to just the lambda eigenvalue space and diagonalize O2. Okay. Does that make sense? Okay. So basically O2 leaves uh, all eigenvectors, or basically it leaves the lambda eigenspace invariant. lambda eigenspace of O1 invariant. Okay, so this is NB2. And so the conclusion is restrict O1 and O2 to the lambda eigenspace of uh, O1 and diagonalize O2. So that's the idea. And then this you can do for every lambda eigenspace. So in all of the blocks, you can find diagonalization of O2. And since you started with an eigenspace of O1, that's already that. Okay. So that's kind of the idea behind this is the proof sketch. Okay. Okay, good. So that is very useful to know. And so once we have this, right, then it's very evident that when observables commute, then the order of the measurement doesn't matter, right? So we can state it a bit more formally, which I leave as an exercise. Okay. So the exercise 27. Oh, by the way, maybe I should have mentioned, I forgot the feedback sheet from the previous lecture. So please fill it if you were here last time. And the one from this time you can fill after the lecture. Okay, so the exercise is the following. So suppose O1 O2 commute, right? Um, and then consider, and you're given some psi. Okay, I'm not writing like very formally. You can look at the notes for the full formal statements. Okay, then consider the following experiments. Experiments. Um, so the first one is you measure O1 first. Uh, measure O1, obtain little O1, measure O2, obtain little O2. Okay. Second one is you do the same thing, but you measure the second observable first to get O1 or O2, and then you measure O1, and you obtain little O1. Okay. And then prove that the probability that little O1, little O2 matches AB when you did the first experiment is the same as the probability that O1, O2 match AB when you do the second experiment. Okay. So it's almost trivial, but it's just good to set up the notation and sort of see. Oh, okay, and for all A, B in spectrum O1. Okay, that's the statement. Okay, good. So this just says that if they're commuting, then indeed, very formally, very properly, we can understand that the order doesn't matter. But what happens when they do not commute, right? Um, so in that case, what we're going to do is we're going to look at uh, the spread in the O1, O2. These are just the answers. This is just a convention. Like you can write them in whichever way, it doesn't matter. The important thing is how you obtain the values. So in the first case, you first measure this, then yeah. Yeah. So experiment 1 and 2 are important. This is just a labeling. You can do it whichever way. Yeah. So it says you measure this and you obtain little O1. And what is? AB are all, so this is the statement. So you have to prove the statement for all AB in the spectrum. So these are the Yes. So you can think of little o1, little 2 as random variables, right? Because you run the experiment, it's a random variable. And now you're asking what is the probability that the random variable, you know, achieves a specific or it has a specific value. Is it okay? Yeah, I just started introducing this notation because we'll use a notation like this for crypto. So I started introducing it in like very, very simple settings. So you basically write the colon, write the process, and then you write the random variables and what values to take. That's the thing. Okay. The statement is obviously completely trivial. There's nothing very deep. Uh, okay. Any other questions? Yeah, there are many notations one can write. It's just that this happens to be very useful because in this case, it's the experiments are very simple, so you could indeed just write capital O1 equals whatever. But in more involved settings, it would just be easier to use this more abstract notation where you just define what the experiment is, define the random variables, and then ask what values they take. Yeah. There's like some iota factors. You have to put like some things to sort of fix it. Yeah, right. Yeah, I also don't actually remember. There's like some double cover. It's not even like a single cover. It's like it wraps around twice. So there are some nice subtleties there. But yeah, but you're right. You have to correct for the iota and so on. And you have to get the correct convention. Yeah. Oh, yeah. Okay. Any other questions? Okay. Okay. So let's move on. Um, so for any observable and any quantum states. Okay. So this is like the story time, right? So I'm going to just give you some intuition first. Okay. So the story is the following. So consider any observable. Consider observable O and state psi. Um, and then you let delta O be the following. So it's O minus expectation O. Okay. Where you call this thing is psi. Sorry, psi O psi. Right. Okay. So what we're doing is we're defining the random variable O and we're subtracting the average value of the random variable. Okay. And the reason for doing this is that when we write delta O square, right? Where was I? Oh, yeah. Then this thing captures the dispersion essentially. Okay. When basically, let's just leave it to that. So okay, so if you're in an eigenstate, right, it's clear that delta O would be zero because you always get the same value. But if you're not in the eigenstate, you're going to get some dispersion. So you'll not always get the expectation value. You might have some deviation. Okay. So psi is an eigenvalue. Okay. Then delta O square. In fact, delta O itself is zero, right? So delta O square would be zero. So this is where we are going to go towards the uncertainty principle. We'll argue that if the observables do not commute, then it cannot be that both delta O for the first observable and delta O for the second observable are zero at the same time. So we'll quantitatively say that there would be a lower bound on the dispersion. And what is the statement? The statement is as follows. Yeah, we'll take the average. Yeah. I was just saying that the operator is intuitively capturing the dispersion. I will write everything under expectation. You're right. You're right. That was your question, right? Okay. Yeah. They're all operators at this point. Yeah. They're all operators. I will talk about expectations of these operators. You're right. Let me write the formal statement. Hopefully, it'll become clear. Of course, you can formalize this in many ways, right? I mean, this is not the only way to do it, but it's one of the standard ways of doing it. And the theorem is the following. So theorem is the uncertainty principle. Which states the following. It says that let O1, O2 be observables, B2 observables. Okay. So, it's on the same system. I'm not writing all of that. Then for all psi, the following holds. It holds. You take the square of the dispersion operator, you take its expectation, take the expectation of the second, so, and you can prove that this would be at least 1/4 the expectation of the commutator, mod square. Okay. So that's the formal statement. And we'll not do the proof where it's not quite relevant, but I thought I'd mention the statement nonetheless, because just for completeness. The proof mostly uses the Cauchy-Schwarz, which will be very useful later as well. So I'll at least mention the inequality, uh, which is that for two vectors, u v and cd, sorry, u v v is at least. Um, and you can sort of see how this would be used, because, yeah, let's not do the proof. It'll probably take us too long. Okay, so that was the uncertainty principle. It quantifies how much dispersion you would have in at least one of the variables. Okay, I will now leave the. So okay, so this was mostly in continuation for the analysis of Stern-Gerlach, right? So we saw how to define the different measurements along x, y, z of angular momentum, and then we looked at commutators. We saw that when they commute, everything is okay. When they don't commute, we figured what the value is. For the double slit, I'll not do the analysis. There's an exercise in the notes that asks you to look at the marks and the interferometer. So okay, so this is section 2.3 point whatever. Okay, here the idea was to apply the axioms to the double slit. Okay, so this is mostly an exercise. I didn't have enough time, I'm sorry. So the exercise basically asks you to first look at what the Mark-Zander interferometer is. I hope I spelled it right. Okay. So to view the double slit, the Mark-Zander is a simplification of the double slit. Okay. A simplification. And then asks you to analyze it. Analyze using quantum physics. Okay. So this we will not be doing now. The next thing we'll work on is the Schrodinger equation, right? So the Schrodinger equation is we'll look at it very, very quickly because in the kind of things that we are going to discuss, we will need a very simplified version or very simplified consequence of the Schrodinger equation, which is just exponentiation, which also you guys know, so we can go relatively quickly. Okay. 2.4. Okay. Um, we'll use a fact uh, from linear algebra, which is Hermitian exponentiation. Okay. So you consider a vector space CD and let UD denote set of all unitaries. Denote all matrices U such that U dagger U is identical. Okay. Um, then it holds that um, UD is actually equal to e to the IH for H Hermitian. Okay. So the set of exponentiated Hermitian matrices is the same as the set of unitary matrices. It's nothing very deep so far. Okay. And and if you define SUD to be U such that U dagger U is identity and determinant of U is 1, then this can also be spanned using exponentiations of Hermitian matrices, except that we want them to be traceless now. Equals H dagger and trace of 8 is 0. So, so Pauli matrices will give you SUT, the fact trace is 0. And this fact, the special fact can be seen by just assuming that they're diagonal. So if you take the diagonal matrix, the sum of the eigenvalues is 0. And for the unitary, the determinant would basically correspond to, it would be the product of eigenvalues, e to the I lambda I, which is the same as e to the I some lambda I, right? And this would be the trace of the Hermitian matrix. So that sort of gives you the, okay. Okay. And then it's the following is a relatively straightforward claim that we know from 11th and 12th, I guess, which is okay. So using uh, the notation in the axioms, right, which I'll not write again. Um, suppose HT is independent of T. Okay, so if it's independent of T, then we know what we know. Then uh, the solution to the Schrodinger equations, which we had written in the so it was like equation 2.1, was what would be the following. So psi at T prime is just e to the minus I, T prime minus T, H, acting on psi at time. Okay. And this just follows from the fact that the derivative of the exponential gives you, yeah, it's just elementary. Okay, so this is good. Okay, so why did I tell you all of this? I told you all of this because this is saying what? It's just saying that you're basically applying exponentiation of some Hermitian matrix, and from this fact, we know that it's essentially just a unitary, right? That there's nothing uh, more that we need. If you're just interested in time independent uh, Schrodinger equation, then it's just a unitary acting on psi, and basically that's the most general thing you can do in this closed system. Okay, so there's nothing. Yeah, so at least for the purposes of this course, we will not need to worry too much about the Schrodinger equation directly, beyond the fact that we use unitary. Of course, not all unitaries would be easy to implement, and we'll formalize what it means for things to be easy or difficult a little bit later when we introduce the circuit model. Okay, so so far we looked at, okay, any questions? This is very straightforward things, but if there's any question, can... Okay, good. Okay. So far we looked at a single system. We can now look at multiple systems, right? Okay. So for this, we are going to introduce some uh, notations. So the idea is that, we had a single silver atom. What if there are two silver atoms? How do you describe the dynamics in that case? So the notation then is going to be the following. So notation 33 is, so we use the word register. So register, okay, so this refers to a quantum system. A quantum system meaning like a silver atom or, pairs of silver atoms or whatever. So a quantum system going to be denoted by uh, you know, Roman letters, basically. Roman X, Y, Z, like that. Okay. And the Hilbert spaces by curly X, Y, Z. Hilbert spaces. I'm just setting up some notation because it would be useful later as well. Okay. So that's okay, good. So with this notation, we are going to define the quantum state on multiple registers. Okay. So definition 34, quantum state on multiple registers. Um, so now given xy, the combined state, the combined or joint state, or yeah, the joint state uh, of the system is given by a vector in x tensor y, yeah, where x tensor y is just the span of u tensor v, such that u belongs to x and v belongs to y. It's nothing very deep happening. And we'll also write uv brevity, or which is the same as u, okay, which is the same as u tensor. This is just for uh, to write things quickly. Okay. And the property of the tensor product that we need, okay, so now story. The property that we need of tensor products are the following. So you have that the dagger would just be u dagger, which is this, right? Tensor v dagger. So they stay in this, the order is respected, but you just flip the bras and the caps. And the other thing is the inner product, right? So if you have u, v, acting on uv, then you get a product of the commutators. Commutators, I'm saying. So you get a product of the inner product. Okay, so that's basically all that we essentially need about the tensor product. Okay, and a very simple exercise is, uh, xi and yi are orthonormal. Orthonormal bases for x and y. Then span of x tensor, xi tensor yj or ij equals x tensor y. Okay? So that's an elementary exercise. Here, I was just saying you take all the vectors in X and Y. Here I'm restricting to orthonormal vectors. So it's almost the same thing. You just have to show that, use completeness of the basis. Okay. Um, and if you're seeing it for the first time, it might also be useful to work out some tensor products, like tensor products of Pauli matrices and so on. So that's an exercise. But yeah, try to do it yourself if you haven't done it before, just to make sure that, tensor products make sense. Okay. So what does that tell us about uh, the dynamics of multiple systems? It's just that you basically use the same axioms, uh, except for, oh, I didn't write it properly here. Okay, so you use essentially the same axioms as before, with two differences. So the first difference is that you need to use, so the state is on whatever x tensor, y tensor, whatever. And second, if individually the states are known to be states are known to be psi I belonging to, yeah, let me call it x1 and so on, say xk. So individually, if the states are psi I in xi, then the joint state has to be psi 1. It's just the tensor product of the individual kits. Okay. So that's just the only change in the axioms that you have to add. Okay, good. And now we can move on to asking a very natural question. Since we've now introduced how multiple systems work, we can ask the question if two systems, if you have a given system, right, and you have an environment like some auxiliary system, you make them interact, and you remove the auxiliary system, then how do you describe the remaining state? Okay, so that's what we'll discuss very quickly now in pure states and mixed states. Okay, so suppose you consider, this is again story for illustration. So suppose uh, Alice, or let's say Alice. Yeah, so Alice prepares psi 0 or psi 1 with probability half. And yeah, so say this is in register X, okay, and sends register X to Bob. Okay. Question is, how does Bob describe the state? How should Bob describe the state? Okay. Right. So it's a very simple thing. And the issue is that the formalism that we've discussed so far doesn't quite tell you how to deal with these kinds of things. Um, you can obviously say with probability half, this is the state, and then use linearity of probabilities and so on, and you can get the answers, but this is not quite, um, it becomes quite cumbersome as you make things more complicated. Okay. Um, so, okay. So then we introduce the density matrix formalism. So here's the definition of a density matrix, right? So you take so S is a register in C to the D. Um, then the state of S is written as, yeah, I think I kind of skipped things a little bit. So here I just wanted to talk about probabilistic mixtures, and then later we'll talk about tracing out environments and so on. So here there was no environment, right? Alice just prepared the same system X in one of two ways and sent it to Bob, and Bob had to describe what the state looks like. Um, so here, so in such situations, one can um, one uses the density matrix formula. So uh, so you write it as follows. So you write that rho is permission, rho is submission, rho is positive. So this means that all eigenvalues are positive. Positive meaning non-negative. Sorry. Okay. And the third is that the trace is one. Okay. So the intuition for this is the following, that uh, so let's write down back to the story, right? So in this case, the description of the state would be P0, size 0, size 0, or it's P1, psi 1, psi 1. Um, okay. And why do we want this? We want this because, suppose Bob measures some observable O. Okay, so suppose Bob measures observable O. Okay. Then the probability that the expected value, then, let's say, then the expected value of O, right? We can write it as follows. So we know that with probability, instead of say probability half, let's say probability P0, P1. Okay. So with probability P0, you will measure using psi 0 or psi 0, right? And probability 1, he'll measure psi 1 or psi 1, right? This is what you get. And um, if you take this as the state and you write down trace row, you get essentially the same expression. So it sort of shows you that uh, that this is a reasonable way. It's consistent with what we expect. So you get P0 trace or actual one size 0 size 0, right? Plus P1 trace or actual one psi 1 psi. Okay. Um, okay, very well. And it's also simple to see how the axiom. Okay, so this was like one specific example. Given a density matrix, okay, so these are just stories, right? Just motivating what's happening. So given the rho can, because it's a Hermitian matrix, right? We know we can always diagonalize it. So you can write it as some pi, phi I, sum over I. And then one can apply the axioms for quantum mechanics for each phi I individually. And then because it's a probabilistic mixture, we can, and probabilities are linear, we can essentially just use this. So everything checks out. Um, and similarly for, the only other thing we saw was unitary evolution, right? So if there's anything at all, like any process at all that happens on this file, uh, then the corresponding mapping for density matrices would just be, we do phi I, and then the dagger E phi I dagger somewhere. So you don't really need to change anything once you know how the thing happens on individual systems. Okay. But there is a little caveat. So the caveat is that density matrices are not uniquely they cannot, then there's no unique decomposition. So the caveat is, um, so rows don't admit a unique decomposition. Okay, so here's an exercise, which is that suppose rho is defined to be 3/4, 0, 0, plus 1/4, 1, 1. Okay, and sigma is defined to be half UU plus half VV, okay, where U is defined to be 3/4, 0, plus 1/4, 1, and V is 3/4, 0, minus 1/4. Okay, and the question is rho the same as sigma? So I think, so that's one exercise. The other exercise is to check the other exercise is to check that, so rho has rank 1 if and only if the state is pure. So pure state meaning, it's described by just one psi. Like we had earlier. Okay, it's almost by definition, but okay. Okay, very good. Now I'm going to introduce a little bit more notation because it would be useful later. So we'll look at some, so we'll just define some sets. Okay, so X and Y are vector spaces as we've been taking them. And then we define linear operators. So the set of linear operators is going to be defined as L, X, Y is, linear operators from X to Y. Lx would be operators from X to X. Unitary operators, so these are unitary operators. Commission operators would be X, right? And positive semi-definite operators are going to be pos X. Okay, so these are just matrices that are Hermitian on X such that eigenvalues, M is positive. Basically, all eigenvalues are non-negative. Okay, so that's the notation we use. And we can now look at reduced states and purifications. Good. So we understand density matrices. We can now look at 2.3.2.2. I'm sorry, guys. I know it just has to be done once to make sure everyone has the same level. So, sorry, but it's boring. But so my goal is, if I'm not able to cover everything I want to cover, I'll just like make a little video and send it to you guys, and then you can watch it, and so we don't have to spend much more time on these things. Okay. Okay. So yeah. So now the story, right? So the story now is, suppose you have a system S, and this is your system. You have E, that's your environment. Okay. And you ask, suppose initially, suppose rho SE was the initial state. How do you describe the state of, how does one describe the state of S locally, right? Without invoking the environment. And this is where reduced density matrices come in. Okay. Um, okay, so now we'll define what's called the partial trace. So the partial trace is the following. So let MSE in uh, LSE. Okay, so it's an operator in S cross E. So we define trace E of MSE as follows. Take EI on MSE EI, where EI is uh, a basis, orthonormal basis for right, the environment. Okay, and equivalently, one can write. So one can write trace E as S prime E, and so sorry, system E prime environment is going to be the same as SS prime. So this part stays unchanged, and then you just do trace of E prime. Okay. So yeah, this is in terms of the vectors or whatever. The tensor product directly. This is in terms of the matrix. So one can always write this. So this works. Okay. And here's some notation. So when your SE belongs to is a density matrix, then rho S defined as says E, rho SE is a reduced density matrix. So this is just like nomenclature. So it's a reduced density matrix. Oops. And the exercise is to actually check that you do indeed. So prove that rho S is indeed a density matrix. So you have to prove that it's positive and that the trace is one if the initial matrix is trace one. Okay. Okay. So now, yeah, so this basically answers that question. How do you describe the state of S locally? Well, you describe it using a reduced density matrix. What is a bit unfortunate, sorry, what is a bit more interesting is proving that the partial trace is the unique correct operation here. So I'm not doing the proof. There's the proof is in, so you can look at box 2.6 of Nielsen and Schwang. This is with the reference to the 10th edition. But the box might have changed the numbering. Um, okay, so this shows why partial trace is the correct operation. Okay, now one thing is clear, right? That Alice doing, you do anything on the environment that should not affect the local description of S, right? This is just sanity check. Otherwise, you can start signaling and things. So this you can check is satisfied by the partial trace, right? Because regardless of what you do on the environment system, right, it will not have, because it's a basis, so it doesn't in the end influence the outcome. Yeah. Okay. So that's as far as we are going to talk about density matrices. Um, and then there are some exercises that ask you to write down the density matrices for various states. Um, which I guess I'll not explicitly write here. I'll just leave the exercise number maybe. Yeah, one day we'll just have a tutorial, so we'll go through all the exercises as well. But depending on, if people actually need some help, or maybe I'll have an office hour for the exercises, depending on, yeah, maybe an office hour would be better. Okay. Um, so now, yeah, let me actually write down the exercise number at least. Sorry, one of the exercises at least, which is the following. So, okay, so first, psi A tends to psi B. Okay, so if this is the pure state, what would be the reduced state for reduced state on A? Yeah, it's completely trivial. I know. I'm just okay. The second one is P0, 0, and psi 0. That's P1, 1, psi 1. Third is 0, 0, plus 1, 1, pi root 2. Okay, so this is AB, P, AB, AB. Okay. Okay. Yeah, who wants to do the first one? Completely trivial. Yeah, maybe one person can do all of them. No volunteers? Do it. It's simple. It's completely obvious. No? Are you just shy, or is it it's obvious, right? For everyone or not? Show of hands if it's obvious. Come do it. Yeah, yeah, do it, do it. It's good. It'll be a little interactive. I'm just sitting and writing things. It's getting very boring, so it'll be good. Just write it for the system A, reduced on system A. So trace out system B. Yeah. Or actually trace out system A, actually, yeah. Remove system A. Keep system B. Yeah, yeah, yeah. Just write the answer. If it's obvious, just write the answer. Yeah, don't worry about it. Uh, okay, yeah. Very nice. Thank you. Yeah, yeah, these are normalized. Assume they're normalized. Right? Yeah, 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 yeah. So these are normal. Yeah, yeah. Okay. Yeah. No doubts, right? Like this much must be like bread and butter for you guys. Okay, good. Um, okay. And now we look at the opposite, right? So we saw how you start from uh, you could potentially start with an entangled state and you remove some part of it and it becomes a mixed state. You can ask the opposite. If you're given a mixed state, can you purify it so that it's a reduced density matrix of some pure state? And it turns out that you can. And there's a nice characterization of all the different ways in which you can do this. So we'll quickly look at that uh, as well. Okay. Okay, so the story is, you know, so let's just say this. So pure states, so you remove uh, part of the system, or remove subsystem. It gives you a mixed state. You can ask, what about going backwards, right? Okay, so here's another exercise. It's about purifications, right? Almost immediate from the statement over there. So suppose, I meant the third exercise, sorry, third item in the in exercise 45. So suppose that you're given row A, and row A is of the following form. So you have lambda I, UI, right? This we can do. Then psi AB, which is just root lambda I, UI. Did I define a purification or not? Okay, actually I wrote it like this. I satisfies trace system B, right? Trace B, trace B, psi equals, right? So it's completely trivial. There's nothing very deep once you know the exercise. What is much more interesting is that that you can essentially have a family of entries. So there exists a family of purifications. So you basically do this, right? I wrote it the other way, right? So all of these would still be purifications, right? It turns out that this is the most general thing you can do. So there's a very nice theorem, which is the unitary equivalence of purifications, which says the following. Um, Let me restart the statements. Let so A be in system A. There's a density matrix, and suppose that psi AB and phi AB in A tensor B are purifications. Okay, so the purifications row A. What does that mean? Um, so that means that if you trace out B, psi, you get row A, which is the same as you trace out B, you take phi. Okay. Then you could prove that then there exists a U in the unitary group on B such that phi is identity on A or tensor U on B. Active. Okay, so here we said that look, there's one purification, I can create many purifications, but that doesn't mean it doesn't say anything about an arbitrary purification, right? It's not clear why this should be true. But the theorem states that if you have any two purifications, they're going to be related by a unitary acting on the auxiliary system. Okay, so that's the statement. Yeah, so let me give you a proof sketch since we've been doing lots of just statements. This one is relatively easy. Uh, and the proof is actually very straightforward once you assume what's called the Schmidt decomposition. The Schmidt decomposition also, I think I have a proof, and I have okay 10 minutes. Let's see if we'll try to do at least one proof. So the proof sketch is as follows. Um, so so you assume so this is a fact. Okay, so every bipartite state can be expressed in this form. Yeah, this is a basis, autonomic basis. This is also an autonomic basis. This is also an autonomic basis for A. This is for B. No, for B. Okay. Um, okay, and AI are strictly positive, right? So you can take some subset if you want. Okay. And similarly, you have phi AB can also be written in this form. So you have A prime I, B prime I, prime I, belongs to Cyprus. I could write capital I as well in terms of dimensions of AB. It's a subset. Because I'm taking AI to be strictly positive, so I'm restricting the summation index. I mean, if I allow AI to also be, I have to keep track of the dimension in the proof. Yeah, so it's a sketch. So at the moment, I'm assuming that A and B are like both purifications have the same B dimension, sort of. Huh? Yeah, it's just a sketch. I'm not giving you like the full proof. Yeah. Um, yeah, the statement might also have to be changed because I'm implicitly assuming that. No, I actually said the purification. Well, okay. So you start with psi AB and there's phi AB, right? And then it's not hard to see, right? So you can write so trace B of psi uh, will essentially be so this is the same as trace B of phi, right? So this we are given, right? So recall. So when you write the trace, if you remove the B part, right, what you're left with is because these are orthonormal bases. So what you'll be left with is uh, AI, UI, right, like mod square, and so this would be this one, and this would be AI prime mod square, UI prime, UI prime, right, and okay, and then what do we have? So then it has to be the case that up to the permutation, it has to be the case that these values match, right? Otherwise, yeah, but up to the permutation, it should match. And why does the vector have to be the same? Yeah, so these density matrices are identical. So okay, I'm assuming that they're degenerate. Okay, so assume AI are distinct. Okay. So if AI are distinct and you have two matrices like this, then it has to be the case that for that all the UIs and AIs have to match. because it's basically like a matrix, right? So you're saying that, like in some bases, this is, I don't know, A1, A2, whatever. This has to be the same, exactly the same as another matrix. So everything has to match if they're distinct. You can do it more carefully. Like you can take inner products with the basis of this with that, and then you can show that it would work. Okay, so the consequence is that, so just this equality basically implies that AI has to match AI prime mod square. Yeah, the mod square is what I'm a little bit concerned about, but that's okay. And then the UIs have to match U prime I. Okay, and the phases I guess you can absorb in uh, the phases I guess you can absorb in the uh, in this in the component on VI. Okay, so then the only freedom left, right? So you have to map basically VI to V prime I, right? That's the only freedom left. Everything else we just proved is essentially the same. And whatever extra phase you might have here, you can absorb it into the V. So you can essentially treat the things. Okay. That's not necessary, right? You have to prove that. Like I could have something which is not orthonormal, right? For example, you can construct examples. I mean, I'm not doing it now, but you can always construct examples where they're not orthonormal. It's still okay. Yeah, but it's not guaranteed that these U's are going to be identical, right? So you can map the I to I, but the U's may be different then. So you don't really, you cannot say that for arbitrary purifications, you can map one purification to the other by only acting on subsystem B because subsystem A might be different. I mean, your argument doesn't say anything about subsystem A. That's all I'm saying. You also have to prove that the subsystem A would be identical in both cases in very deep sense. Okay, so there's one proof. Maybe there are simpler proofs. I'm not aware of them, but this sort of uses the Schmidt decomposition. Um, okay, so in the last 5 minutes, let me quickly say something about entanglement, since we are already starting to see entanglement. Okay, section 2.3.2.3, entanglement. Okay, so so we know that one of the most striking features is entanglement of quantum mechanics. Um, and the statement is, yeah, okay, so there are some examples that are left to work out. Okay, so there's an exercise. I leave the exercise which has a bunch of states listed, and you have to check whether or not you can separate them, and also compute the partial traits. But the definition is the following. So the definition is separable entangled states. The definition is, so let AB denote two registers. See? Um, so then rho AB is separable if there exist matrices sigma I in A and sigma B in B, such that rho AB is the same as uh, for some pi. Okay, where and I is a subset of n. Okay, and if not separable, then entangled. Okay, so that's the definition of separable and entangled. This is just for bipartite. Okay, for multipartite, it's probably a bit more involved. And what is very nice about and there's lots of very nice things about entangled states. What is nice about pure bipartite entangled states is that you can give a very nice decomposition like this. Okay, so uh, yeah, so lemma 50 is the Schmidt decomposition, and Schmidt rank. I'll just state the theorem. I think we don't have the time to give the proof. We'll do it next time, or I'll send you a video. The statement is just what we saw here, essentially. So let me just write it a bit more carefully. So given psi AB in A tensor B, there exists UI VR, orthonormal orthonormal basis, such that psi AB is of this form: CI UI A tensor. Okay, and uh, and the number of non-zero CI uh, is the rank, is the Schmidt rank. Okay, so that's the lemma and the definition. And proofs comes through SVD, but we look at it. It's a very simple one-line proof, so I can explain it next. Okay, so I guess yeah, let's stop here for today. When do I stop the recording? You guys, for the third, uh, just some feedback for me. What? Yeah, for today. Yeah. Yeah. Yes, this.